Harper.
All right, so now we're recording. Psyched to be doing some Ask Dr. Sam with you today, Beckett. I'm going to share my screen with you so you can see what I can see on my screen. And there we go. Hopefully you can see that now.
Yeah, I can.
Okay, so I can't remember if I showed the whole class this movie about why stars shine last week. But it's kind of some important information to know about in terms of what supernovae are. But I can just summarize it for us now, and we can come back and watch this movie later on. But basically the idea is that stars are these gigantic nuclear power plants. They're these huge balls of hydrogen and helium, the simplest atoms, the simplest elements that exist in the universe. And they're so hot and so dense in their cores, in their centers, that they can smash these atoms, these simple elements together, and they make them stick. And when they do that, they give off energy. And that's the light that we see from the sun and all the stars in the night sky, and it's all the heat that we get from the sun. And after a long time, the stars run out of all of their fuel. They run out of all of these elements that they need to produce energy. And after they run out of fuel,
They turn into a black hole.
some of them do, the very biggest ones. And so it all depends on how big the stars were when they started. So this diagram here shows you all the different ways that stars can be born. So some stars are born really, really small, and they have cooler temperatures, and so they have kind of a reddish color to them. Other stars are born really, really big, and they're much, much hotter, and so they look kind of bluish when you see them in the sky. And that's just how they start. Stars change throughout the time that they exist. And so these really, really big stars, they move along this pathway during their existence, and they end up as these red supergiants. And those are the ones that go supernova. And so you may have heard of a star called Betelgeuse. So Betelgeuse is one of these giant stars up in the sky right now. It's a red supergiant, and it's going to explode sometime soon. Sometime between tomorrow and 1,000,000 years from now. And that's the best that we can say. Sometime in the next 1,000,000 years, Betelgeuse is going to explode. And when it explodes, it's going to create all of the things that exist in the universe in terms of the different elements, the different fundamental pieces of things that exist in the entire universe. And I'm going to show you a picture of that. I can find it here. Here we go. So you probably haven't seen this in school yet. This is called the periodic table of the elements. It shows you all the stuff that makes up all the other stuff in the universe. So for instance, this H right here in this box stands for hydrogen. So hydrogen is most of what exists in the universe. Every star in the universe is made up mostly of hydrogen. And then the next most abundant element is helium, He. So stars are mostly hydrogen and helium. And only the very, very biggest stars, the biggest stars that exist in the universe, in green here, can make all of these other elements inside of them because of how hot and how dense the stars are in the very centers. And then only when those stars explode as supernova, in this color right here, do all the other elements in the universe get created. Gold, silver, platinum, lead, all the really, really heavy stuff that exists in the universe. Those elements only get formed when a star explodes as a supernova. So that's what a supernova is. It's a giant exploding star. Stars that are much, much bigger than the sun. And I want to show you how much bigger. We're talking a lot bigger. So I want to show you this little movie here, and it's going to show you just how big some stars are. And I'll pause it when we actually get into the stars that can go supernova. So first it's showing us dwarf planets. And then it's going to go up to planets, or first the moon. We're still looking at moons here. Callisto is a moon of Jupiter. Now the planet Mercury, that's the smallest planet, since Pluto is now a dwarf planet. There's Mars. Mars is about 1/3 the size of Earth. There's Venus. Venus is roughly the same size as Earth, just a little bit smaller. There's the Earth, mostly water on its surface. That's why it looks dark blue. This is an exosolar planet. It's a planet that orbits around another star, Kepler. There's the planet Neptune, a lot bigger than the Earth. And Uranus, just a little bit larger than Neptune. Okay, there's Saturn. See that Saturn is way bigger than those other planets. Jupiter is even more huge. So you could fit about 1,000 Earths inside of Jupiter. 1,000 planet Earths in Jupiter. Okay, so now we're into stars. Proxima Centauri is one of the smallest stars that we know about. It's also one of the closest stars to us. You can see it's tiny compared to the sun. See how tiny all the planets are down there. There's Sirius A, that's a bigger star. Okay, so now we're getting up into the stars that can actually go supernova. Vega is still a pretty young star, so it's not going to explode anytime soon, but it's big enough to explode. Stars like our sun can't explode. They're not big enough, but Vega is. So one day, millions or even billions of years from now, Vega will explode. But now we're going to see some stars that are much closer to the time that they're going to explode in the next couple million years. Okay, so there's Betelgeuse. That's the star that I was talking about that's going to go supernova sometime soon, sometime in the next million years. So you can just barely see the sun. It's just a tiny little yellow speck way down there, just barely. So Betelgeuse is so big that if you put Betelgeuse where our sun is in the solar system, our sun would be right here in the middle, and Saturn would be right here. All the inner planets would be inside this star if it was where our sun is. That's how big Betelgeuse is. And it's not even the biggest star. But that's how big red supergiant stars are before they explode. They get really, really big. So now let's see some other ones. Okay, so what you're seeing right here is a black hole, but we can't actually see black holes, so it just looks like a big black circle. But you can see how much bigger black holes are compared to stars. Even the largest stars are tiny compared to black holes. So this object right here is called a planetary nebula. It's what our sun will look like after it runs out of fuel and then gently poofs its outer layers out into space. So it's not a supernova. It's not an exploding star. Stars like our sun can't explode. They don't have enough mass, but they do just kind of more gently puff their outer layers out into space. And that's what we're seeing here. Okay, so this is a different type of nebula. This is a stellar nursery. So in this big cloud of gas, stars are actually being born. And we can see this object up in the sky in the winter. It's in the constellation Orion. It's just down below Orion's belt. And even with a pair of binoculars or a small telescope, you can actually see this object. And right in the center of it, where it's so bright, there are baby stars being born and planets being formed around those stars inside this giant gas cloud. So this is a different type of object. This is called the globular cluster. So it's a huge collection of stars packed really tightly together because of gravity. It's not a galaxy. These globular clusters actually exist inside of galaxies. And there can be thousands or even millions of globular clusters in each galaxy, in every galaxy. And so this one is inside the Milky Way, in our galaxy. But it's just a huge cluster of stars, really, really old stars. Some of these stars are almost as old as the entire universe. This is a dwarf galaxy. This group of stars actually orbits around our galaxy. It goes around the Milky Way just like the moon goes around the Earth. There are lots of satellite galaxies like that. And this one is a dwarf galaxy because it's kind of small compared to other galaxies. There's our galaxy, the Milky Way. That was a really big galaxy there. This is a part of space where we don't see anything. And that's the entire observable universe. It's the part of the universe that we can see. And all these weird colors here are what's called the cosmic microwave background radiation. It's the radiation left over from the explosion that we call the Big Bang that created the universe. And what we see today in our night sky using special telescopes is this stuff, the evidence left over from the explosion that started the universe. So you got to see how big stars are that go supernovae, that explode, and then you get to see how small they are compared to galaxies, compared to the entire universe. All right, so what questions do you have now?
So I was also going to ask you, since You said that since you said that Ceres was the biggest asteroid in the asteroid belt, what is the biggest asteroid in the belt orbiting around Saturn? Because the belt orbiting around Saturn is ice and rock.
Yeah, you're absolutely right. It is. So that's a tricky question to answer because, as you mentioned, the belt itself, the rings around Saturn, are made of chunks of ice and rock. And there are also small moons that keep those rings in place. They're called shepherding moons. And some of those moons are really tiny, and others are quite a bit bigger. There are some moons of Saturn that are bigger than our moon. And it's hard to say like where the rings actually end and whether those moons should be included in the rings. Let me see if I can find a good picture here to show us. Just to describe what I'm talking about here. We need a really close-up picture of Saturn's rings. Let's see here. So I want to show you some of these shepherding moons. Okay, so here's one interesting picture. Yeah, this is good. Okay, I'm gonna grab this picture here. I'm gonna add it onto the slideshow so you can see it. Just give me one sec here. Let's see, you should put it right down here. One second. There we go. All right, I'm gonna make it bigger. All right. Hopefully this is big enough so we can actually see it. Try and make it a little bit bigger for us. So what I hope you can see here, there are all these rings, and then there are these moons. So Enceladus is one of the moons that's like out in the outer ring called the E ring. So Enceladus is a pretty big moon. It's not as big as our moon around Earth, but it's way bigger than any of the asteroids in the asteroid belt, including Ceres. And so I think you'd have to include Enceladus in the rings of Saturn. Let me see if I can find a comparison of Enceladus and Earth's moon, just so you can see the size comparison. Let's see here. Oh, there we go. That's really good. Okay. I'm going to make another slide here. Save this image. And we're going to put it right here. There we go. All right, so it doesn't show you a comparison of Earth's moon, but it does show you how big Enceladus is compared to the Earth. So maybe it is actually a little bit smaller than Ceres. Now I'm looking at, see, where's that picture of, so there's the Earth in Ceres. Yeah, it might be around the same size, actually. So the cool thing about all three of these moons Europa and Ganymede are moons of Saturn, or excuse me, moons of Jupiter. Enceladus is a moon of Saturn. These are all moons that potentially have life on them. We don't know if they do or not, but they might. Make it a little bit bigger here for us.
Do they have an atmosphere? Because you have to have an atmosphere to have life.
Well, there won't be any life on the surface of these moons because you're right. These moons don't have an atmosphere, but they do have an icy crust on them. And we think underneath the icy crust, there's liquid water. We think there are huge oceans underneath the surface of the ice in these moons. And so it's possible that there could be life way deep down in the oceans, just like there's life in the bottom of Earth's ocean. So even though they don't have an atmosphere, so they can't have life on the surface, they might have life underneath the ice layer. So we're not totally sure yet, but it's possible. I think we had a question with our other guest here. You remember your question down there?
Yeah. What would you see if you went into a black hole?
Great question. So as you got close to a black hole, this is what you would see. If you got really close, then all this bright part around the black hole is what we call the accretion disk. It's this big disk of material that's getting broken apart, stars and planets and everything else. As it orbits around the black hole, it heats up and it starts giving off light. That's why it has this reddish, whitish color. So before it gets sucked into the black hole, we can actually see it. So that's what you would see as you got close. And then as you got even closer, what would happen to you is that you would get spaghettified. As you got really close to the edge of the black hole, the part of you that was falling in first would start to get stretched out more than the part farther away from the black hole. So you get spaghettified. You get stretched out. If you actually lived through that, which is debatable, but if you did, there are basically three different things that you might see in a black hole. One would be there'd be kind of like bright flashes of light all around you, but most of it would be dark. But you might see these bright flashes of light. That's one possibility. Another possibility is that there'd be just so much light everywhere that it would just be kind of almost totally white. You just see bright light completely filling up the black hole, so you wouldn't be able to see anything really. The third possibility of what's inside a black hole, you couldn't actually see this, but we think that what's possible is that the smallest things that you can possibly imagine might be in the center of a black hole. They're called strings. They're not the actual type of string that you have in your cabinet, but they're these tiny, tiny little things called strings that make up all the other stuff that exists in the universe. And they might actually exist in the center of black holes, and what's called the singularity of a black hole. So those are the possibilities. It could be mostly black with some little flashes of light. It could be totally full of light, so you wouldn't be able to see anything. And when you got down to the center, you might be able to detect these little things called strings. Great question. So what other questions do you guys have?
Is that Ayla? Oh, good. Hi. Oh, did you want to ask your other question back? About the tides?
Oh, why is the solar eclipse Why is a solar eclipse only a couple years? Only a couple years, like every 12 years or so. But it should be only a month because the moon rotates around the Earth 1 month. So
Great question.
So why
Yeah.
doesn't the eclipse, happen every month?
Yep, that is a great question. I'm going to find a picture that can show that to us. Let's see here. Trying to find a really good image that, no, that one's close. Let's see. Okay. That's kind of one good possible. Trying to find a really good image for us here. I think this one is probably the best. Yeah, let's do this one right here. Or actually, I really like this one. Okay, here we go. Now I found a good image for us. I'm going to save this image. Okay, and let's see. Put it right here.
It just doesn't smell right, and so I'm seeing both price cash, and so I just send an email out.
There we go. Make it bigger for us. Okay. So why don't eclipses happen every month? So the reason is that the Earth and the sun and the moon don't line up perfectly every month. You are correct that the moon goes around the Earth once a month, and that once a month it actually passes between the sun and the Earth. But as you can see here, the lunar orbit, the orbit of the moon around the Earth, doesn't line up with the orbit of the Earth around the sun. It's tilted. And this tilt is exaggerated here. It's only about 5 degrees off. But that 5 degrees off makes it so that even when the moon is perfectly in between the sun and the Earth, the shadow of the moon doesn't always line up in the right spot. So I'm going to show you what I mean by that.
So it like basically goes under or over the sun?
Under or over the Earth. Yeah, and I'll explain what I mean by that in a second here. Let me get this next image in here to show you.
Right.
Then I think it will make more sense. Okay. So here's a picture of sometimes the shadow being too low, like you said. So when the moon isn't lined up perfectly, the shadow of the moon wouldn't be right in the middle of the Earth. It'd be down here. Let me show you how everything has to line up for us to get eclipses. There's another really good image here.
Oh, so sometimes it goes over or under the sun's light?
Well, it's the shadow of the moon that has to hit the Earth perfectly for there to be a total solar eclipse. I'm going to show you this next picture, and I think that'll help you understand a little bit. Get this next one in here.
So here's the thing.
This is a really good picture.
Well, yeah.
There we go. Get that out of our way.
That targeting has smaller brokerages.
So,
My question too is that
for there to be
you had some issues with them.
a total solar eclipse, this shadow of the moon has to contact the Earth just like this. So that would be a total solar eclipse, when the shadow of the moon hit the point on the Earth. And for a lunar eclipse, the shadow of the Earth has to be on the moon. So that's when the moon lines up perfectly in a straight line between the sun and the Earth. When the moon's up a little bit too high or down a little bit too low, you can see that the shadows don't line up. The shadow of the moon is just up above, or it could be just down below the Earth, or the Earth's shadow can be just up above, or it could also be just down below where the moon is.
Right.
So that's why we don't get an eclipse every month. If the moon was lined up perfectly, with the orbit of the moon was lined up perfectly with the orbit of the Earth, then we would get an eclipse every month. But because the moon's orbit is tilted at about 5 degrees, it only lines up like every once a year on average.
Oh, you're right.
Great question.
Oh, absolutely right. And
Yeah,
it's
go
like
for it.
between
What's your
us,
question
but-
down there?
That's the thing is
How
like,
big is the entire space?
I don't know, I'm not sure what to do. I just feel like we need to.
Say that one more time.
How big is space?
How big is space? Great question.
Right.
Space is really, really big. There's a little video here that'll show you how big space is. But first, let me explain a couple things before we watch this
Well,
video.
you can have it, it's an ethics.
Use,
it's an ethics issue. I mean, I guess you could use
There's a
it.
term called a light year, okay? And so a light year is a distance. It's the distance that light can travel in 1 year. And that's a really, really long way. 1 light year is 6 trillion miles. Okay, so the size of the valley that we live in, Jackson Hole, is about 6 miles across. And the distance between here and Idaho Falls is about 60 miles, 60. And the distance between here and California is about 600 miles. But a light year is 6 trillion miles, a 6 with 12 zeros after it. So it's a really long way. That's how many miles 1 light year is. And this movie is going to show you that the universe is actually 93 billion light years across. Not just 1 light year, which is 6 trillion miles, but 93 billion of those miles. So let's watch this video.
How big is the universe? Everywhere you look, there are stars. These are in our galaxy, the Milky Way. Light takes 100,000 years to cross our galaxy. If the whole of our solar system, including the vast bubble of comets surrounding us, was the size of a toilet cubicle, the Milky Way would span the distance from Greenwich to Maidstone. Beyond the stars are even more star cities, galaxies of different shapes, colours, sizes, stretching out across space for billions of light years. The closest big galaxy to us is Andromeda. If we sent a text message out to aliens in Andromeda, it would take 2.5 million years to reach them. When we look at galaxies through our telescopes, their light might have taken millions or billions of years to reach us, by which point they would have aged and they might not even exist anymore. It's as if we're trapped on a desert island. We experience a horizon in all directions beyond which we can't see anything. However, our cosmic horizon is receding all the time as light eventually reaches us from farther and farther galaxies. This is like waiting for photos to be delivered to us from distant parts of the Earth whilst on our desert island. Unlike our earthly ships, light travels at a whopping speed of 300 million meters per second. But even light takes a finite amount of time to reach us, and this sets our current cosmic horizon What can we actually see with our telescopes? Well, we can't see light from the birth of the universe. The early universe was a very hot, small, dense place where light continuously bumped into matter. About 380,000 years after the Big Bang, the universe was large enough and cool enough for atoms to form and for light to travel freely through space. This includes the ancient radiation from the Big Bang, which we can see in all directions. After about 200 million years, the first stars formed, and then galaxies, and then eventually the Milky Way, including our solar system. If the lifetime of the universe was a 10-hour movie, humans would only appear in the last second of the film. Remember, during all this time, the universe has been continuously growing over a period of 13.8 billion years. That's 3 times the age of our solar system. So does this mean that the universe is 13.8 billion light years big? The answer is no. When light first left a faraway galaxy, it was much closer to us, but over time, the universe has expanded like a huge balloon. So the light has taken longer to reach us. Over large enough distances, space can expand faster than the speed of light. This means that signals sent from one galaxy to another would never reach their destination, forever beyond contact. Imagine the universe is a stretchy sheet. If we pull it in all directions, we can find out how much it's stretched by if we know the original size. To explain the current size of the universe, scientists think space rapidly inflated just after the Big Bang. It continued to expand at a much slower rate, slowing down further due to the gravitational pull of new young galaxies. We can calculate the real size of the universe by taking into account all of the matter and the energy present and its current rate of expansion, and another mysterious component. We've seen that very distant exploding stars called supernovae are dimmer than expected, and this tells us that the universe is bigger than we thought, and it's getting bigger at an ever-increasing rate. So, what's causing this anti-gravity effect? The exotic, mysterious component of our universe that cosmologists have introduced is called dark energy, which acts as a gravity repellent. Gravity is still fighting strong and holding together galaxies, stars, and planets. Over large scales, however, dark energy wins, pushing everything out and away from everything else until eventually starbirth will become impossible. So based on all the information we currently have, the proper size of the universe is 93 billion light years across, or 884 billion trillion kilometers, or if our solar system was the size of a toilet cubicle, it would span the distance from Earth all the way out to Venus. Pretty big, eh?
So, the universe is really, really, really big. Unimaginably big. I can't really wrap my head around how big the universe is. It's beyond what our brains can actually do. A great question. What other questions do you guys have? Yeah, go for it.
How did the Big Bang happen?
Well, that is a really good question, and nobody knows. We have no idea how the Big Bang happened. Let me see if I can find a little picture that actually shows how the universe has changed over time. Give me 1 second here. Let me see if I can find this image.
Okay, you have to stop knocking over my computer.
I'll show you guys.
Your video's frozen.
Let's see here. See if I can find this picture I'm thinking about.
There you go.
Give me 1 second here. I'll find it for you guys.
Okay.
It's in here.
No, see, this is up.
Let's see here.
Yeah, it is there. Okay, perfect. Thank you.
There it is. Okay. So this kind of shows you how the universe has changed over time. And like I mentioned earlier, we don't know why the universe started with a Big Bang. We don't know what caused the Big Bang. What it says back here is quantum fluctuations. And what that means is that really, really small stuff, smaller than you can possibly imagine, sometimes that stuff happens without any reason. It just happens. And we think that maybe something like that actually started the universe. So there may not have been a reason that the universe started. It may have just happened for no reason at all. But first it was really, really small, and then it got super big, and then it slowed down in how big it was getting. And recently it started getting bigger faster. And that's where we are right now. We're right here, where the universe is expanding faster and faster. It's getting bigger all the time. And we think it's going to continue to accelerate. It's going to continue to speed up in how fast it's getting forever. So it's going to be even bigger as the future moves forward. Great question. What other questions you guys have?
I don't have one.
Okay. Yeah, go for it.
The Big Bang could have been caused. Sorry, that's my baby sister. The Big Bang could have been caused by a black hole. It just got.
Yeah, you're absolutely right. Some astronomers think that there might have been an ancient black hole.
Yeah.
And that ancient black hole might have actually given birth to the entire universe. We don't know if that's actually what happened, but yeah, there are some astronomers who think that that might actually be the real deal. Great idea. I'm impressed. Yeah, go for it, Beckett.
Why when things go into a black hole, why do they get stretched out?
Oh, that's a great question. So it has to do with the same thing that makes the tides happen on Earth. So here's a picture of what are called tidal bulges. The gravity of the moon kind of pulls on the Earth. It pulls the water of the Earth in one direction or the other. And so the gravity in a black hole does the same thing. It pulls the stuff of whatever is falling into it in one specific direction. And those tidal forces are so strong that they affect the different parts of something that's falling in differently. So the force that you feel on your feet is stronger than the force that you feel on your head. And so your feet get pulled in more strongly than your head does. That's why you get stretched out. Great question.
So like basically your head in like the outer space is pulling you away from the black hole, and the black hole is pulling you into the black hole, so you get stretched out.
Yeah, it's not that there's a force pulling you away. It's just that the force of the black hole is strongest on your feet.
And like there isn't any force and there isn't much force up here, so like it kind of makes the black hole slow down on pulling you, which makes you stretch out like a rubber band.
Yeah, I think you got the idea. What other questions do you guys have? Yeah, Ayla.
What if you fell out of? What would happen if you fell out of the bottom of a black hole?
Ah, very interesting question. So We're not really sure, to be honest with you, because nobody has ever fallen into a black hole, and we've never sent any spaceships into black holes. They're too far away. But there are a couple possibilities of what might happen. Let me see if I can find these pictures. Odd, I brought one over. Maybe I forgot to do it. Okay, so I'm going to bring a picture over, which will show you what potentially might happen. But we're not totally sure.
I'm fine, so I have 2 more birthdays. Who's that?
Hang on one step.
My birthday got from how do we open this thing? Oh,
Okay, here we go.
hi, little horsey. Here. He's so small.
Oh, hold on, it's in a different language. Oh, here's a good one.
I'll just be right back. I'm gonna be right back.
Okay.
There's nothing really to do.
Save that image.
This is my mom's office. Don't make too big of a mess, okay? Is that a blankie? Yeah, it's huge. Do you want to feel it? That's
Here.
How about we can make like a 2-person bed?
Here's that picture. Okay.
Okay, can you move over that? Sure.
So, here's one idea of what might happen. So here's a black hole over here. And this over here is what's called a white hole. It's the opposite of a black hole. So one possibility is that you might actually pop out a white hole.
If you want.
You could pop out into an entirely different universe, or you could just pop out into a different part of our universe. But we're not really sure which. So this is what it would look like if you popped out into an entirely different universe. Let me show you what it would look like if you just popped out into a different part of our universe.
Gotcha. Oh, wait. Do you have the pink one? Sure. What to?
One sec here. Here comes the picture.
Sure.
Here we go.
How about this can be our technically space next to us?
So these things are called wormholes.
Right there.
And we don't actually know whether they exist or not.
Okay, let's get a bed.
But if they do, they might be able to transport us to different parts of our galaxy or different parts of our universe. And we might actually get there instantaneously. You could potentially travel faster than the speed of light by traveling through a wormhole. So it would kind of look like you were falling into a black hole, but then you fall out the opposite, which is called a white hole, someplace else and maybe some other time.
Can I hold it?
Just don't know yet.
Thanks. Oh, just get down, you.
That's kind of what it would look like. You'd fall in one direction and fall out in another direction.
You just stay in your bed and we'll give you some breakfast.
Yeah, go for it, Beckett.
Can black holes collapse like stars can collapse?
They don't collapse, but they do evaporate. So let's see. You can actually see it here. So everything that comes near a black hole falls into a black hole, and nothing actually leaves a black hole. But black holes have a temperature, and just like anything else that has a temperature, heat can escape a black hole, and it escapes in these really long jets. And so over a really, really long time, trillions of years, all the energy, all the heat that a black hole has can escape from those jets. And eventually it just disappears. but it takes trillions of years for that to happen.
Nails are getting off.
So black holes can evaporate.
Okay.
Yeah, really good question. Let's see if I can actually find a real picture of that, because it's pretty cool. Let's see here. Oh yeah, here's the classic picture. This is a real image of, oh, that's not the right one. This is a real image of the jet of a black hole.
Let go of my sister's flip flop. Oh, sorry.
Here's a really good one.
A dog's got my sister's flip flop.
Whoopsies.
Drop that slipper.
Drop that.
Drop that.
Okay.
Drop. Drop it. Drop it. Drop it. Drop it. Drop it.
No.
Drop.
All right. So this is what they really look like. These big jets that I was talking about from a black hole.
Gotcha. How about if you just hold the tail?
Put this, hold on one sec here. I'm gonna put this
Drop
in front.
it. Drop it. Yeah. Drop it. Drop it. No. Don't get the unicorn. Drop it.
So this is a really special galaxy,
Drop it. He's smacking me with his
Messier
tail.
Object 87. And this picture was taken by the Hubble Space Telescope. So the galaxy is right here.
Ow.
And in the center of this galaxy is a huge black hole. And you can see the jet
Get out. Get
of
out.
material leaving the black hole.
Out.
So that's how
Out.
black holes evaporate.
Get out. Close the door.
By
Yeah,
giving off
because-
those jets.
Yeah, because they lose all of their material.
Yep, in the form of energy, just heat,
Now, get
high energy particles.
Well, wait for unicorn. Gotcha. Put her to bed.
How do black holes swallow stars? Wait, like what would happen if a black hole tried to swallow a star that was bigger than the black hole itself?
Well, it's a good question. There aren't any stars bigger than a black hole.
But like
But-
what would happen if there was a star bigger than a black hole, or a black hole was formed smaller than a star?
Well, here's the thing about that. So the universe, for reasons that we don't totally understand, has rules about how big things can be and about how small things can be. So there are upper limits to how big stars can be, and there are lower limits to how small black holes can be. If a star gets too big, it becomes a black hole. That's the only thing that nature allows. When stars get too much mass, they collapse in on themselves, and they become black holes. And black holes can only form when there's enough mass concentrated down into a small area. So the smallest black hole is always larger than the biggest star. But there could be a star, let's say, half as big as a black hole. And if that star got too close to a black hole, it would get ripped apart. Let me see if I can find a movie of that.
I'll be right back. You just
Might be a good movie or something that we could watch of.
Well, like, what would happen if a star got really big, but then it stopped getting bigger, like right before it turned into a black hole?
It would just be a huge star. All right, I think I've got a good. Let's see if this video is actually going to show us. No, this is too complicated. Let me see if I can find a better one here.
Green is my favorite
Oh, okay.
color.
I think this is
That's correct. End of day tomorrow.
this is good. Let's see here. Oh yeah, here we go. Okay, this is a pretty cool video. Let me bring this video onto the slideshow here.
So that I know
Then
how
we
to
can take a
stand
look.
on it. There's 1 minute.
1 second here.
Mom, I just need to get something. Need to get something. No, no.
Here we go.
No. Get out of here. You use the back of this paper and I'll use the back of this paper. Hey. Wait for me.
Okay, 1 second.
The unicorn needs me.
All right, let's check this out.
I'm very good at drawing.
There's the black hole.
Be safe.
That was pretty cool.
Drawing a unicorn.
Let's watch that again.
Yeah.
I like that. Yeah, here comes the black hole. Do you see it down there?
Yeah.
Stretching the stars around it. Here comes the star. There are the jets that we talked about earlier. Okay, how about one more time? There's the black hole. So
Why doesn't it?
you can see how
why
the
does-
black hole is like bending the light of stars behind it. So this is really cool here because it's showing us the accretion disk, and this part right here where we can't see anything more, it's called the event horizon. Once you pass the event horizon, not even light can escape a black hole. Out here it would still be possible to escape, but once you pass this point, that's it. Everything gets sucked in. What were you going to ask, Beckett?
Oh, I was going to ask. I pretty much forgot.
That's okay. When you remember, you can let me know.
Wait, I remember.
Okay.
So remember how it was like making the stars around it go just like around the black hole?
Oh, yeah.
Why didn't it suck up those stars
Ah, great question.
instead of just pushing them out of its way?
Yeah, I know it looks like it's pushing those stars out of the way. Actually, what you're seeing are stars really far behind the black hole. And the black hole's gravity is so strong that it's actually bending space. So it's actually working like a magnifying glass and distorting the images of the stars around a black hole. I'll show you a better picture of that so we can see it.
Oh, I thought those were just tiny stars.
No, they're really, really distant stars. Find a good picture. But Ayla, what's your question?
Can a black hole spit out some stuff like a jet, or like kind of make a noise or something out of it, like burping out some star?
Yeah, it wouldn't make noise that your ears could hear, but it does make noise when like a black hole hits another black hole. When black holes combine together, they do this thing called creating gravity waves. They actually make these waves through space. And even though our ears can't hear those gravity waves, there are really special telescopes that can hear those gravity waves.
That can hear them?
Yeah, well, kind of like hear them. Special telescopes that can detect the ripples in space, and they convert those ripples into sound, so we can actually listen to it. But it's not like real sound like we hear it. Yeah, this video is pretty cool. We'll show you the gravitational lensing that we just saw. Going up onto another slide for us.
No.
Oops, that's not what I wanted.
Come on. I thought you were going to play with me. Come on, let's play. Yeah. That's your little unicorn.
So it's called gravitational lensing. When it acts kind of like a lens. And I'll put this video in here for us. Okay. Yeah, 1 second here. Okay.
We should go to bed now. It's kind of late. Let's go to bed.
I'm gonna get it right in the center for us.
Here. Tell Stu.
There we go.
Pretend your bed is over there with that little blanket.
Okay.
My bed's over there.
All right, here we go.
Go. Pretend your bed is
Our team's backgrounds span a range of disciplines: fine arts, graphics, engineering, science, photography, and
Pretend your
theory.
bed is right over here.
What we shared was an opportunity and desire to create beautiful, physically accurate images of a black hole.
Then the unicorn is getting asleep, Mommy.
Driving force behind this work. The key part
So there you go.
was the development of double negative gravitational lensing. This computer
see all the
code creates
stars seem
images
to
by
be
modeling
moving,
the path of light
but it's
as
actually the
influenced by the immense
gravity of the
gravity
black hole
The
that's
light
just
originates
bending
either a
the
distant
images
star
that we
or
see.
from an accretion disk, a hot glowing disk of gas orbiting the black hole. The gravitational lensing causes the accretion disk to appear to wrap over the top of the black hole shadow.
And it's gravitational lensing that's causing this shape too.
Swirling patterns.
It's actually
The camera
behind
focused
the
the
black
hole.
hole, this
Sometimes
top part.
images of stars get amplified in brightness.
I want to go to my mom.
A pair of images merge and annihilate.
That's what we'd really see
from
a long way away.
Iconic images of the black hole seen in the movie.
And that's what was in the movie
What was novel
Interstellar.
about the code was using beams. Previous work was concentrated on tracing really thin rays of light to an IMAX movie. One thing we noticed about our beams was they gave a very clear depiction of Einstein rings. These rings are the images of galaxies or
I'm gonna have to watch the rest of that right now. But yeah, that's the weird stuff. Ooh, yeah. So here's what happens when two black holes merge together. This is super cool. Let me show you this one.
Cell phone.
Okay.
I got this.
Oops.
Play for a little bit.
not black hip press.
Nope. There we go. Black holes merging together. Now make that centered. And I'll make it front.
Oh yeah, that's mine.
And we want to be able to see the title, so we're going to make it white. Now we'll bring that movie in there. There it is. This is super cool.
I was holding this.
I
and
know.
then
If you break my computer.
I didn't mean to.
So this is how we get gravitational waves.
I'm not gonna touch this.
Okay, stop touching the computer.
Okay, I'll try not to.
On my way.
There is it.
All right. So now you get to see what happens when two black holes come together.
Can I
That's
go
cool.
back to my mom?
Of course, sweetie.
So we've never actually seen this, but we've detected the evidence of it through gravity waves. And you'll see the gravity waves ripple out when they come together. So they're orbiting each other, getting closer and closer now, distorting all the background stars behind them. Yeah, so see that like really small ripple that happened at the end, kind of like a wavy pattern through space? That's a gravitational wave. And we actually detected those on Earth.
Can we watch it again?
Yeah,
To see?
yeah, it's pretty cool, isn't it? Pretty cool, huh?
So they just turn into a bigger black hole?
Yep, yeah, they just become a bigger black hole. Let me see if I can find a recording of the sound that they make.
Be quiet, I need a phone.
Here we go.
Hey everybody.
Hold on. It's like a news station. I don't want a news station. Let's see here.
We're talking a lot about black holes.
Well, black holes are pretty cool.
This is the sound of two black holes.
Oh, cool. Okay, here we go. I'm gonna bring up this next video of like the sound of two black holes. This one's pretty cool. Get this video. Bring it in here for us. Here we go.
Call.
Yeah, this will show us like all about how we actually got the sound of black holes all the way to Earth.
Oh, yeah. Bye. There we go.
Okay, here we go.
I'm late for school. Bye-bye.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our sun, were locked in orbit and spiraling towards each other. The only visible traces of this spinning cataclysm have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in this system was in the form of gravitational waves, rippled through the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merging to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
You can go ahead and get it done. Sit down here. If we have it, if he says no, then you can go.
That was pretty cool.
Otherwise, you're gonna have reason. Just have to prefer witness because it's reasonable. Either way, we're gonna.
Can we watch that again? I like that.
Yeah.
Hi.
Hi, Papa.
Have you guys had lunch? Hi,
Let's take
Katie.
out this other one because we're not
How
going
are
to need
you?
this one now.
How's your new baby boy?
All right, here we go.
Is he your brother? Oh, I see that.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in the system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything that passed through it, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
Mercedes was
Go for it, Ayla.
What if a black hole merged together? The two black holes merged together that had already merged. Like black holes that merged together.
Yeah. So we think that that's happened. We think that the giant black holes in the centers of galaxies are lots of black holes that have merged together. So we think that happens all that time. They just keep getting bigger and bigger. huger and huger
This is the school.
as they merge together? Great question.
What would happen if like more than 2 black holes combined, like 18 black holes combined, or
Like all at
12?
once?
Yeah, like 12 or 18 or
It would just
25.
Yeah, it would just be a way more complicated signal, a way more complicated sound. Let's see if I can just bring this right over here so you guys can see that. Can you see that now?
Yeah.
So if this is what it would look like if 2 black holes came together. If it was lots of black holes, there would just be way more jagged lines here. The signal would just get way more complicated. But I think basically it would look the same. But to be honest, I'm not totally sure. I don't know if there's ever been, I don't think there's ever been a detection of more than 2 black holes merging together. I think we've only seen 2. But it's possible for more. Yeah, Ayla, go for it.
What if suns merge together?
What if stars came together?
Yeah.
Yeah, let me show you that. So typically what happens, you have one really big star and one smaller star. And the smaller star is actually denser, and it starts pulling material off the big star. And eventually, the small star pulls off so much material from the big star that it explodes as a supernova. Let me see if I can find a little video of that. Give me 1 second.
Like, but what would happen if 2 stars the same size emerged?
I think they would probably detonate as well. I think they would probably explode. We don't see that happening very often. Let's see here. Let's try this one right here.
There's like a pilot people. I've been really good. All right, we're running away. I'll let you guys.
Nope, that's not what we want.
Daily planner.
Oh, I know.
Nope. Hang on. Let's see here. Still looking for a good video here. Here we go. I think this will work.
The luminosity of a supernova depends on the mass of the star.
Okay. Yeah, this video is good. I'll bring it over here for us. Maybe I'll just link it right in here into the title. I think we should just do that. Just do that. There we go. Okay.
The luminosity of a supernova depends on the mass of the star. If we knew the mass, we'd have ourselves another standard candle. But for most explosions across the cosmos, we don't have that information. But there is one scenario where we do. It's called a Type 1a supernova. It is based on a particular binary star setup, and it is recognizable via light profiles and spectral analysis. Here's how it works. 1. A massive red giant star has a small stellar companion. 2. Mass flows from the giant to the dwarf through the L1 Lagrange point. You'll remember Lagrange points from our discussion in Jupiter in this segment on our solar system. 3. The mass of the dwarf star increases. 4. Once the mass of the smaller star reaches a critical level, its ability to hold off collapsing under the force of gravity comes to an end. The result is a total.
So you guys maybe remember what I was talking about earlier, that nature has limits on how big things can be or how small things can be. So there's a limit of how big these small stars can be. They're called white dwarf stars. And once they get to be more than 1.44 times the mass of the sun, so almost 1.5 times the size of the sun, they explode. So we always know exactly how big they are when they explode. Now we'll get to see that.
Total collapse inside a few seconds. This creates a supernova explosion that rips the smaller star to pieces.
Say goodbye to Harper. Hey, maybe we can play in a couple days. Harper and Beckett won't be here tomorrow, but they'll be back on Friday. Yeah, do you want to try to play that?
So that's what happens when you get two stars coming together.
Maybe next time you can bring some waters that you guys can go.
Yeah, Ayla. Wait, I couldn't hear you. Hold on. Let me mute Beckett. I can't hear you. Try one more time.
Would all the dust, what if two moons came together? Would all the dust make a dusty thing so we couldn't see it, or would?
Yeah, so I mean, Earth only has one moon, so we don't have to worry about another moon hitting our moon. But yeah, I mean, there are planets that have lots and lots of moons, and potentially their moons could hit each other. And yeah, when that happens, you get a lot of dust and a lot of debris. I can actually show you a movie of how our moon formed, and it'll kind of show you just how much energy gets released when something like that
Mama,
happens.
watch this. Mama, watch this. He's going to show us how our moon formed.
Let's see if I can find it here.
Mama, come on.
Let's see. Oh yeah, it's in here.
Watch this.
I think it's this one right here. Yeah, here we go.
Let me take you back to the earliest days of our planet. 4.5 million years ago. At this time, the Earth had no moon. It was orbiting the sun alone, and it was being assaulted by rocks and comets.
Mama, watch. Let's watch.
There are no scars left from this cosmic pinball. But to get a sense of the damage that was done, I've come to the Arizona desert, to a great hole in the ground.
This is a beautiful crater, a near-perfect circle, a mile in diameter. It was formed when a meteor crashed into the Earth a mere 50,000 years ago. That's nothing on the timescale that we're talking about. But it's amazing how much damage that one passing rock can cause. The early Earth was bombarded with rocks. It must have been mayhem. And then along came something much, much bigger.
Another planet, the size of Mars, drifted into the path of Earth. It was on a collision course.
Glancing blow. Imagine the power released by such a collision.
The impact sent a mass of liquid rock into orbit. This debris coalesced into a ball, and the moon was formed. Just 14,000 miles away from the early Earth. This was the closest point it could have been. Any closer, and gravity would have pulled the debris crashing back to Earth, and there'd be no moon. Today, the moon is just a rock, reflecting the sun's light. But back then, it was a molten sphere, burning brightly. It must have looked amazing, an enormous golden disk in the sky. Imagine imagine the scene. The first moonrise over the early Earth. Our world was no longer alone. It had a huge, powerful neighbor. And ever since, this has been a very different type of planet.
Pretty cool, huh? Yeah, go for it, Ayla.
Why doesn't the moon show in the daytime?
Oh, it does sometimes. You just have to be really sneaky and know where to look. Let's see here. Maybe I can bring up a, let's see. One sec. Yeah, here's a little video.
Practice.
Let's see. Yeah, I think this is really good. This will tell us a little bit about how we can see the moon during the day. Bring this one over. Let's see here.
Oh, Harper's laying down there. We're right now. Okay.
How much time do you need for me to review it?
All right, let's check this out.
Hey guys, Weeks and I love looking up at the sky. Clouds, airplanes, the moon, there's so much to see. And one clever SciShow viewer recently asked us a really interesting question about the daytime sky. 8-year-old Dawson wants to know, why can I see the moon in the daytime? Great question, Dawson. It does seem kind of strange. Sometimes we think of the moon as something you only see in the night sky. But that's not true. The moon is always hanging around. Sometimes it's out at night and sometimes it's out during the day. And much of the time it's visible for parts of both the day and the night. That's because the moon is on the move. And so is Earth. You probably know that our planet, the Earth, is spinning around in place, kind of like a toy top. As it spins, half of it faces the sun, and the other half faces away from the sun. The part facing the sun gets the sun's light, and for that part of the world, it's daytime. And the part facing away from the sun doesn't get any light. There, it's nighttime. But things don't stay like that for long, because the Earth is always spinning. And every time our planet spins all the way around, that's one day. Okay, so the Earth is always spinning, which makes different parts of the world go through day and night. But what's the moon up to? Well, the moon is also moving. It's traveling in a path around the Earth. We call this movement orbiting. And it takes about a month for the moon to orbit the Earth one time. So the Earth is spinning and the moon is orbiting. But the most important part about why we can see the moon is the sun. That's right. The sun makes its own light, sending heat and warmth to us here on Earth. But the moon doesn't. The only reason we can see the moon is because it's also getting light from the sun. That light bounces off the moon and comes down to us. So in order to see the moon, we have to see the side of the moon that's being lit up by the sun. Just like the Earth, the sun only lights half of the moon at a time. And since the Earth is spinning and the moon is orbiting, we see that lit up half of the moon in different parts of the sky and at different times of the month. Sometimes the lit up side of the moon is facing the nighttime side of Earth, so people there can see the moon in their night sky. But as the moon slowly moves in its orbit, day by day, it swings around so that more of its lighted half is facing the daytime side of Earth. And when that happens, We can see the moon during the day. Now remember, it takes about a month for the moon to go all the way around the Earth. That means that for part of the month, you'll see the moon more in the daytime. And for the other part, you'll see it more at night. And maybe you've noticed when you look up at the sky that the moon doesn't always look like a big circle. Sometimes the moon looks like a cookie with a bite taken out of it. Other times it looks like just a thin little fingernail clipping. And sometimes it looks like a big round plate. But the moon isn't really changing shape. It's just very slowly moving around the Earth, giving us different views of the side of the moon that's being lit up by the sun. So if you're a sky watcher like Dawson and Squeaks and me, then keep an eye out for the moon during the day and at night. And ask questions, just like Dawson did. When do you see the moon during the daytime? And when can you see it mostly at night? And how does the moon's shape seem to change during the month? And while you're at it, if you can see the moon, take a picture and send it to us. We'd love to see it. Thanks for your awesome question, Dawson. If you have any questions about the stars or the ocean or robots or monkeys or anything at all, ask an adult to help you leave a comment below or email us at kids@thescishow.com. We'll see you next time.
Excuse me.
Yeah. So that makes sense to you, Ayla?
Yeah.
Go for it, Beckett.
How is the moon full when it's behind the Earth? Because the Earth's shadow should be covering all the sunlight.
Yep. So remember how we talked about earlier where the moon isn't always lined up directly in the same line as the Earth and the sun? So let's see if I can find that spot where she shows us the moon perfectly. Let's see here. Okay, so this is really good because she's showing us like where the moon is around the Earth. Actually see in the sky. So the sun's over here. So the daytime side of the moon is there. And if we were standing on the Earth up here, this is what we'd see. We'd see the daytime side of the moon from our perspective. Okay? So a little while later, I don't know if it's going to be all the way full. Let's see. Pretty close. Okay, there we go. So now it's all the way full. So now the sun is still over there, Earth's still here, and the moon is right here. So now we can see the entire daytime side of the moon. So if the moon was lined up perfectly flat between the Earth and the sun, you're right. The Earth's shadow would fall on the moon. But typically the moon is a little bit above or a little bit below that line. And so the Earth's shadow misses it. And we just see the full daytime side. That's the trick that they don't show here. But if you can imagine if they took this image of the Earth and the moon, and instead of seeing it like this, they rotated it like this, and we were seeing it on its side, you would see that the moon would be a little bit down below where the Earth and the sun is. And that's why we don't get an eclipse every month. Great question. You guys must be getting hungry for lunch.
I'm not really hungry.
No, I'm getting hungry. What's your question, Ayla?
Is there any actual water on the moon, or was there any water on the moon?
Yeah, there is water up there. It's just not liquid water. It's frozen water. Let me show you this really cool video that NASA made. NASA is the space organization that puts people on the moon and creates spaceships. I want to show you this movie that they made about going to the moon. And
I've went to NASA before.
Oh yeah, that is so cool.
Yeah, I watch NASA television.
Oh, nice. That's awesome. Well, maybe you guys have already seen this movie, but I think it's super cool. They describe how they're making new missions to go to the moon right now. See if I can find it. It's a super cool movie. Yeah, I got it. Hang on one sec. I'm going to bring it into the slideshow here for us. I'll just put it with the rest of my moon links. Put it. Oh, and then I should totally show you guys this other link of these astronauts walking on the moon. It's so cool. Okay. This is my favorite NASA movie right now.
50 years ago, we pioneered a path to the moon. The trail we blazed cut through the fictions of science and showed us all what was possible.
Very pretty out here.
Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production
and more in testing,
this system is capable of being the catalyst for deep space missions.
We need a capsule
that can support humans from launch
through deep space and return safely back to Earth.
For this, we've built Orion.
This is NASA's next generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources.
We're currently developing an entirely new approach to landing and operating on the moon.
Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and to stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable,
that can land anywhere on the lunar surface.
The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
An orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits.
It will balance between the Earth and Moon's gravity.
In a position that is ideal for launching even deeper space missions.
In 2009, we learned that the moon contains millions of tons of water ice.
Okay, that's one of the reasons I wanted to show you guys this video. So this is a satellite image of the moon, and all these blue patches are areas where there's water ice. So there's lots and lots of water ice on the moon. We don't know exactly how much, but there's tons and tons and tons. So all we have to do is heat it up and make it into liquid water, and then we can use it. So we know that it's up there. It's just frozen in ice right now.
This ice can be extracted and purified for water. It can be separated in oxygen for breathing or hydrogen for rocket fuel.
The moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we're building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire endeavor, and yet we go for humanity. We go to the moon and on to Mars to seek knowledge and understanding and to share it with all. We go knowing our efforts will create opportunities that cannot be foreseen. We go because we are destined to explore and see it with our own eyes. We turn towards the moon now, not as a conclusion, but as preparation, as a checkpoint toward all that lies beyond. Our greatest adventures remain ahead of us. We are going.
We're going.
We are going.
We are going. We're going.
Pretty cool, huh? Okay, you guys get to see this movie of astronauts walking on the moon, and it's pretty funny because they actually trip a lot. Turns out that it's really hard to walk on the moon.
Okay, as I stand out here in the wonders of the unknown in Hadley, I realize there's a fundamental truth to our nature. Man must explore.
One of the things you got to stop and do, make sure you have fun too, because you're only probably going to come this way once.
I was floating on the moon in the merry, merry month of December. May, when much to my surprise, a pair of bunny eyes. Do-do-do-do-do. Oh, is this a neat way to travel? Isn't it great? Dum-da-dum-dum-dum. 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 I like to skip along, but me, boy, skip. Or whatever you call it. I can't get my left leg in front of me. Dum-da-dum-dum-dum. Dum-da-dum-dum-dum.
It was almost dangerous. You lose sight of the fact that it's a vacuum out there, and if you spring a leak next to it, you're going to be dead.
Uh-oh. Nice soft baby landing. Yahoo! Oh. Ah! Boy, do I like to run up here. I feel like Bugs Bunny. That's neat. And here comes the Foxy twin. You're pretty agile there, Twinkle Toes. I'm going out for the ballet when I get back. You learn another line of work up here. Yeah, while you're bouncing around there, you might keep an eye out for a nearby crater. Oh, rat. I've been on my knees twice to get there. John? Yes, sir. You are black from the knees down. No way to avoid it. That's why I'm glad the pressure suit bends. John, you are filthy. I tell you, there's a spot called the Kill Black. Hey, here's a rock I'll be glad to see in Houston. Man, until you don't know how much fun this has been. We concur, John.
Pretty cool, huh? You guys want to be on the moon someday?
Yeah. Sorta. Like, you know.
I definitely do. I would love to go up to the moon.
It's like I want to experience what it's like up there, but you know, if you spring a leak or something, there's no way to fix it.
Yeah, you got to be careful. That's for sure. But I think I could pull it off. Yeah, Ayla, what's up?
Can our moon, what would happen if we didn't have our moon? What happened if our moon just disappeared?
So if our moon just disappeared, we wouldn't have the tides. And I know that doesn't really mean much for Wyoming, but if you live in a place like San Francisco or New York or any place where there's an ocean, the ocean comes in and out all day long and all night long. And that's because of the pull of the moon. And so if we didn't have the moon, we wouldn't have the tides. And the tides are related to lots and lots of different creatures that live right by the seashore. And so they probably couldn't survive without the tides. And then we wouldn't have any light at night from the moon. When the moon is full, you can almost read by moonlight outside. So that's pretty cool. And so, yeah, I think things would be totally different at night. if we didn't have a moon up in the sky. But other than that, oh, you know, the other thing that would change, we wouldn't have a 24-hour day. The length of the day was partially set by the fact that we have a moon going around us. If we didn't have a moon going around us, I think the day would be longer. I hope I'm getting that right. Let me do a search to make sure I'm right.
Like how much longer?
Well, I'm gonna do a search and find out. Let me figure this out. Would the day be longer or shorter without a moon? Let's see. Okay, let's see if we can find a good answer for us here. Okay. Let's see. Still reading here. All right. Okay, so the Earth would spin faster without a moon, so our day would be shorter. Let's see.
But why does the moon slow down the Earth's rotation?
It's because of the moon's orbit. So these tidal forces that you can see right here on the screen, so these tidal forces actually pull energy away from the Earth. So just like when you spin a top, you have to take energy from your hand to make the Earth spin, or to make the top spin. So the Earth absorbed energy from the formation of the solar system for it to spin. But when the moon is going around the Earth, it pulls on the Earth, and it actually slows down that spin. It pulls energy from the spin of the Earth.
Like how much shorter would it be?
Yeah,
like,
so that's what I'm looking at right now. Let's see.
2 hours, 5 hours?
Yeah, so what it says right here in this
3
article that I'm
seconds?
reading, it says that the Earth's cycle of day and night would be less than 10 hours long. So instead of 24 hours to spin all the way around, it would be less than 10 hours to spin all the way around.
That would be a very short time to sleep and a very short time to play.
That's right, 5 hours of daylight and 5 hours of nighttime, and that's it. That's pretty cool.
Jeez.
It'd be like, I'm going to sleep. Oh, now it's morning time. It'd be like, it would feel like 16 seconds.
Yeah, I think the days would seem to be a lot shorter. I'm gonna add the link to this website in here because it's such cool information.
If we lost the moon, since if we like all of a sudden the moon just got pulled away, we would like go to sleep and sleep for like 3 days.
Well, let's see. I think it would take a long time for the rate of spin to change, our rotational speed. I think it would take thousands and thousands of years for it to change. I don't think it would happen overnight, but over a long time period, yeah, it would start getting faster and faster. The spin would speed up, and days and nights would get shorter.
Until it would be like,
day would be like 3 seconds, and you're like, I didn't even get upstairs. It's already nighttime.
I don't know if it would ever get that fast.
Well, there is a possibility after like 3,000 million quadrillion years, it would be like, I haven't even got downstairs, and it's nighttime already.
Yeah, so here's something interesting to think about. So there's something called being tidally locked. So the moon is tidally locked to the Earth. And what that means is that we only ever see one side of the moon. I don't know if you guys have ever noticed that, but even though the moon is rotating and the Earth is rotating and the moon is orbiting, we only ever get to see one side of the moon. There's always one side pointed away from us and one side pointed towards us. And so if we didn't have a moon, there is a chance that Earth could have become tidally locked to the sun, which means that only one side of the Earth would have daytime and one side of the Earth would have nighttime. That's possible. That'd be pretty wild, huh?
But why does the moon keep the Earth from not being tidally locked to the sun?
Because it's tugging on the Earth. So if the moon never formed at all, there's a chance that the Earth could have become tidally locked to the sun. Not a very high chance, but it's possible.
So like one side would always be facing the sun, and like you'd have to go all the way to the other side of the world to have nighttime.
That's right. Yep. Yeah, pretty crazy, huh?
I don't hear you. Watch 10 right now.
Well, let's take about 10 more minutes to answer any questions you guys have, and then we should probably go eat some lunch.
I don't have any more questions.
No?
Everything I was thinking to say to you, you answered.
Oh, nice. Well, I'm
So
glad I was able to do that.
I don't have any more questions.
Okay, and it looks like Ayla left as well. Maybe she went to get lunch. Well, Becca, it's been a lot of fun.
Hey.
I hope you enjoyed asking all your questions and getting some answers. Oh, hi, Ayla. Do you have another question?
Yeah.
Okay, we said we're going to take like 10 more minutes and then we'll wrap it up.
Okay. What will happen once the solar system gets destroyed?
So that's when the sun runs out of fuel and the sun becomes a planetary nebula. When that happens, all the planets will get destroyed. But that's not for another 4 to 5 billion years. So we got a lot of time. But yeah, it's just a natural thing that happens with every solar system. They form, they exist for a while, and eventually they get destroyed by their stars. And then we become a planetary nebula. Let me see if I can show you a picture.
What is a planetary nebula?
Yeah, so it's the leftover stuff of a sun-like star. Let's see if I can
But
find.
why would the rest of the planets get destroyed just from when their sun turns into a cloud of gas?
Good question. So the first thing that happens is that the sun expands outwards. And so it gets really, really big. And our sun will get big enough to expand all the way past the orbit of Mercury, past the orbit of Venus, past the orbit of Earth, almost all the way to the orbit of Mars. So all the inner planets will get cooked by the sun. And then eventually the sun poofs out its other gas layers, and that gas is really, really hot. And it's moving away with a pretty hard force. And it will hit the outer planets, the gas giant planets, and probably rip them apart. See if I'm trying to find an image of what that's going to look like. Thought I had one saved here. Now I can't. Oh, there it is. Here we go. Okay. Can you guys see that picture now? Or not yet?
No, not yet.
No, it still says tidal bulges.
Okay, I'm gonna bring up this other picture now for you.
Okay.
How about that?
Yeah, I can see that at least.
Yeah. So this is what our solar system is gonna look like in probably 4 to 5 billion years. This is what our sun will be. This tiny little white dwarf star in the very center, and all the inner planets will be gone, and all the outer planets will get destroyed by this expanding super hot gas cloud as it moves away from the sun. That's what we think is going to happen. I mean, we know it's going to happen eventually. And then it'll continue to expand and take all of the stuff from the solar system out into space. And eventually it'll bump into another cloud and it'll become the stuff of a new generation of planets around a baby star. So everything gets recycled in the universe. So everything that exists in our solar system will someday become the parts of another solar system. And there might be somebody like me giving this talk to a couple kids like you 8 or 9 billion years from now, talking about how they're made up of the leftover star stuff from a solar system that existed billions of years ago. Kind of cool to think about that, huh?
Yeah.
Yeah.
Well, that's probably a pretty good place to stop. Okay, Ayla, last question. Here we go.
Why does what would happen? What would have happened if the big boom hadn't happened?
That's a really good question. I don't have a really good answer for you. If the Big Bang didn't happen, I don't think we'd be here having this conversation right now. The whole universe might not even exist. I mean, that's the moment where we think the entire universe started. Without the Big Bang, there might not even be a universe. Nobody really knows. That's a pretty cool question, though.
What if our sun collided with another star?
You know, something like that supernova that we saw, but the chances of 2 stars actually colliding is pretty low. So when we watched that movie, we were watching stars that are called binary stars. They're stars that form really close to each other and they orbit around one another. So our star is not a binary star. The sun is kind of all off by itself in space with the planets, but no other stars around it. But binary stars sometimes combine, like we saw in that Type 1a supernova video. But the chances of 2 stars actually randomly hitting each other is really, really small. There's just too much space out there. Stars are really, really far apart. The chances of it happening are small, but if they did, I mean, there would be an explosion. They definitely explode. Well, thank you guys so much for all your awesome questions. That was a lot of fun. And maybe we can do this again sometime.
Thank you so much.
Yeah, you're really welcome.
Such a great session. We're going to go watch the SpaceX launch right now.
Oh, cool.
Yeah.
What's that?
Oh, you're going to love it, Ayla. It's pretty awesome. You're going to see a rocket launch.
No.
All right, you guys have a good afternoon.
We appreciate it. Thank you so much, Samuel.
Oh, yeah, it's my pleasure.
All right, bye-bye.
Bye.
See you later.
Bye, Beckett.
Bye.
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 See you guys next time.
What you want?